Thank you.
You're welcome. You're welcome. You can see my screen, right?
Yes.
Okay, let me try and return it to white theme here. So we are going to talk about decision trees. So let me try by maybe defining what a decision tree is. A decision tree is a supervised or labeled data machine learning algorithm that can be used for both classification and regression problems. It's similar to the tree data structure. I think this one you have come across tree when you say like a tree data structure, that if you say this and you go this way, if you say this you go the other way. So it's similar to that, which has a root and multiple other types of nodes. So basically, I don't know if you have one here. So this is the root. I don't know if you can see my cursor, like the root node, and then usually have like should I say the baby's node or what? These are the other nodes here. So basically, that is what this statement is all about. The first one, the parent, child, and the leaf. So decision trees are a simple supervised machine learning model, which essentially means that the model has to be supplied with labeled training data using which it can make its predictions. So we need like to supply it with training data, just the way that we've been doing since we started with linear regression and then multiple regressions. So basically, it works.
I think there is something that is not opening on your end because of Google Colab.
So can I open it?
Yes, there's an image here that was very important.
Should I open Anaconda or VS Code can do that?
I'm not sure, but I think you should open in Jupyter Notebook.
Okay, let me try and open the Jupyter Notebook. So there we have the image of the decision tree, Linda. What do you have there?
Yes, it's a decision, like it's an illustration of what you've been. So it forced you to go to down there, and they placed it. Yeah.
Okay, let me open my Anaconda and then see how it works. So as my Anaconda is continuing to open, the decision tree, it works in a greedy top-down manner, starting from the root node or the parent node, containing some n numbers of branches and ending with leaf nodes. Anaconda is opening up. So it is continue to open. Before we build our first tree, it's worthy learning a bit about what they are and how they work. Below is a diagram showing the conceptual structure of a decision tree. So before I continue, let Anaconda open. I'm used to using Colab and VS Code. I think I need also to go back to Anaconda.
Has it opened? I can share for a minute.
Yeah, you can share. It's still opening.
Okay.
Maybe you can scroll up, Linda.
Just a minute.
Okay.
So this is the start. So in short, if you are talking about a decision tree, most of the time a decision tree is usually supervised. And if you are talking about something that is supervised, mostly in machine learning, something that is supervised is something that has like the data is already labeled, as compared to the unsupervised. If you talk about unsupervised, here data is not labeled. So a decision tree, they're just saying that it's a supervised labeled data machine learning algorithm that can be used for both classification and regression problems. This means that when you're dealing with regression problems, like a problem that is related to regression, then you're advised to use a decision tree. And also, if you are dealing with classification problems, then a decision tree comes in handy for you for solving that problem. So they're saying that when you are dealing with decision tree, most of the time it's just like in a form of a tree structure. You see, like the way you usually have a tree, it has the root, it has the leaves, and it has like the parts. But now when it comes to a decision tree, there's the roots, then you have the nodes, which are the parent, the child, and the leaf. So these are just like the simplest supervised learning model. That means that the model has to be supplied with labeling training data used when it makes decisions. Yeah. So here's an example of just an illustration, maybe to show you how maybe a decision tree looks like. So we have the root node, which is always like the source of where you are coming from. Like, for example, if you want to make decisions, that is where you are coming from first, like the base. Then from there, now you'll have decisions in between. Then at the end, you'll have the terminal nodes, or sometimes they're also called as the leaf nodes. Yeah. So I think I'm done. Mm-hmm.
So thank you so much, Linda.
Pardon?
Thank you for that good explanation. Unless someone has an answer. As a question, sorry.
Yes, yeah, but it's labeled, but remember they're saying supervised. So if something is supervised, that means it is labeled. Any machine learning model that is supervised, meaning it's labeled. And yeah, so that means it has the response variable, which is dependent, and also which is the target variable. Yeah, so that's true. Yes, Ferris, that's true. It's like inverted, yeah.
Okay, thank you so much, Linda, for that. So, in simple terms, decision trees are like tree-like machine learning models which represent data by partitioning it into different sections based on questions asked of predictive variables in the data. To make a decision on a new point, we start at the root node, and this is the root node, the one that have been shown, no? which is at the top of a upside down tree. Ask questions at each decision node about the attributes of the input. At each decision node, these are the decision nodes. So at each decision node, we usually ask questions for us to make a decision. The ones that are in, which color is that? I don't know. As long as I've seen the color, I don't know. I don't know if it's orange or pink. I can't see now. So ask questions at each decision node about the attributes of the input. Then repeat 2 until we reach a terminal node, also known as the leaf node. Repeat 2. I think this is 2. So you're supposed to repeat this step again. Ask questions at each decision node about the attributes of the input until we reach a terminal node. So what are they trying to say here? So if you come from the root node, and then you have here the decision node, we will ask questions, so and then decide whether we shall take this route, or this route. That's the first step. So if we take this route, we will come here. So we need also to repeat the second step at this point here. If we come there, we'll repeat the second step. If we come all the way here, we'll still do the same. If we come here, we still do the same. If you come here, you still do the same. If you come here, you still do the same. So that is basically what that statement is trying to tell us. And then it tells that, and then it tells us until we reach a terminal node, also known as the leaf node, at the bottom of the upside down tree. So these are the terminal nodes where we get the answer that we're looking for, the green ones. Because from here you can see this is where those terminals end, then there's nowhere else that you can go. And then each terminal node in the decision tree contains a potential output, that is y value, for a given input x value. So these terminal nodes here, they can be the answer. Potential, answer, all these, any of them can be the answer depending on our on what we are seeking, right? The y value at the terminal node only becomes the output of our decision tree if the path of decisions on an input x from the root node lead to that particular node. So for example, if we start here and then we made a decision to go this side, so we shall go this side. Then from here, we also need to make a decision because it's still a decision node. Then maybe we decide to go this other side. So from here, then we need to make a decision. Then if our decision is to go this side, then we'll discard this, and then this will be our chosen value, the y value. Though these ones are also still potential y values. Any question up to there? Okay, no question, thank you. Then consider the following example of a new data point x with a value of 4.5. If you wanted to print the y value for this new data point, the path that the input will follow along the decision tree is shown in green color. So let us try and look on this. This green color, right? So here it says, consider the following example of a new data point x with a value of 4.5. So at our parent node or the root node, we need to follow a path where x is 4.5. If we go this way, this tells us x is already greater than 5. And then on this other side, it tells us x is less than 5. So basically, if we take this other path, which says x is greater than 5, then we'll be making a wrong decision, because we've been told here x has a value of 4.5, and here x is less than 5. So it could be 4.99999, 4.84, 4 point something, so we don't know. So we shall take this path. And then when we come here again, we need to make another decision, because this is still a decision node. If we try check here, it tells us x is less than or equal to 2. But if you come here, x is 4.5. So meaning, if we take this road, that won't be like the true path. But here it tells us x is greater than 2. So if x is greater than 2, it could be 3, it could be 4, it could be 4 point something, but it cannot be like above 5, because here it's x is less than or equal to 5, the route that we took. So again, we come to this other decision node here. On this other side, it tells us that x is less than or equal to 4, and our x here still remains 4.5. So if we take this route, we'll be making a wrong decision. And then this other side tells us x is greater than 4, which is basically true according to a value here of 4.5. So if we take this route, then we go to the terminal node where we get our y is equal to 2. So this tells us at that point where our x is 4.5, then our y value will be equals to 2. Any questions up to there from that explanation? Okay, no question. So the value of y becomes 2. In the decision process, data points start at the root node and end at the terminal node. Root node here on the parent node, terminal node here. The training process follows the same pattern. In training a decision tree, we begin with all of our training data at the root node and then partition the data into smaller subsets which form the branches of the tree. So all the data will start here, then it will be partitioned into smaller subsets which will form the branches of the trees. These are the branches, these things that you see here, just like here. Yep. When partitioning the data, two questions need to be answered. The first one is, which predictor variable should be used as the split criterion? And then the second question is, what value of the predictor variable should be used as the splitting point? Linda, do you mind explaining this too? Or Nehemiah, as you welcome you. Oh, you are in a meeting, sorry.
Okay, the two parts.
Yeah.
So like the first one, if you talk of which predictor variable should be used as the split criterion, like you are looking at the x values, like the x1, x2, all the way to xn. So that is what you are partitioning. Then you are trying to ask yourself if the two questions need to be answered. So which predictor variable should be used as the split criterion? Like you're moving from x1, x2 as you move down to check maybe where the split will be. Like for example, the way you've been moving from x, and then you are looking if it's greater or equals to 4.5. Then you split and continue moving down. Then what value of the predictor value should be used as the splitting point? So like for example, here just go up. Like for example, here you started by on the image. Yeah, like for example, here you went ahead from the root node, then you are checking if x is greater or equals, if x is equals to 4.5. Then you realize that x can never be, it's not greater than 5. So you left away the branching on this side, then you took like you made a decision to go the other side. So that is what you are doing for the first one. Like you are looking which predictor variable are we going to split on. Then you went ahead to make another decision to check if it's x is less or equals to 2, and then x is greater than 2. So you see which one are you splitting on? You are going to split to x is greater than 2, because now x is greater than 4.5. You see? Then again, you go down again. You move, then you also check, you make also a decision. Then you get x is greater or equals to 4, then x is greater than 4. Then you realize that is to then terminal. So for the second one, what value of the variable do we use to split? Now our y becomes 2. I've seen somebody ask why our y is 2. Is because the first place you made the decision for you to arrive at y is equals to 2 was when you chose x is greater than 2. So that is y is equals to 2. Unless Jebet was also helping us. So unless any other person or Jebet can help describe that.
Maybe the only thing I can add is which predictor variable should be used to split the criteria. So, for example, we are having multiple predictor variables. Let's say we want to predict whether we are going to play, considering how the day is. So, whether it's windy, whether it's we are looking at temperature, we are looking at cloud, and we are looking at rainfall. So, deciding which among the three you'll choose to split at. That's the first point. And then the second point, in which value of that attribute are you going to split in? Is that just like that?
So, Ijoma, has your question been answered? Yes, Lauren.
So I'm trying to understand this point 2. So the value of the predictor variable, assuming that we have a data set, then we've taken the first step, which predictor variable. So we've said we want X1. So in that X1, we have maybe 1,000 rows. So is it safe to say that what value of the predictor variable is one of those 1,000 rows in a data set perspective?
Yeah, I think so, because you're talking about you're having various variables of xi's, right? X1 up to x maybe, and right?
Yes.
And then in that column,
X1, X2, X3. So the first step let's say we've chosen X2. We are dealing with X. So now we are dealing with X2 column. So in that column of X2, the value of the predictor variable should be one of those rows.
Yeah, for example, maybe our X2, we are looking at where X2 is 4.5, right? And maybe because in that whole column, we are only having X2 values. Maybe they could be 3, 7, 5 to 1, right? So we need to make like the value of that predictor variable, of that predictor variable. Our predictor variable we've already identified is X2, right?
Yes.
Then what is the value of that X2? Is it 3? Is it 4.5? Is it 7? So it needs to be one of those values, from my understanding. Yep. Now, unless someone else can also add on that. We are so many here today. So somebody else, Abdikadir, Ijoma, anybody can try and explain more. Okay, we good. We go ahead. Then here we come to partitioning. Partitioning in regression trees involves dividing the data at each node into two subsets through recursive binary splitting. So we are dividing the data at each node into two subsets. If you try and look, sorry guys, let me put this on here. The power is on. Yeah, if you try to look at this root node, we have divided the data into two. This side, where x is less than or equal to 5, and then the other side. At this decision node, we still do the same, dividing the data into two. If you can check on this picture, we're just dividing the data into two. The only point we are not dividing the data is at the terminal node, because it is at the end. So this is basically what is this sentence is talking about. Maybe Jebetu can explain recursive binary splitting.
Recursive is just we are repeating the same, like we are repeating twice until the end. Like we're asking ourselves, is it like this or like this until the end? Like we're repeating the question until we reach the final reward.
Thank you. This process entails evaluating potential binary splits for each predictor variable and selecting the split that maximizes data separation. The optimal split point is determined based on its ability to minimize the mean squared error for each side of the split. I don't know how to explain this.
Yeah, I think I can explain that. I think I wish I had the, how is it called, the Jamboard, but it's okay. So what happens here-
let me open it.
Okay.
Like that
Okay,
whiteboard for sharing.
Yes. And maybe you can give me an access so that I can
Yeah, let
just
me.
while it's there. So if you share it, I think I can continue explaining. So you see the way Jebeta said, like recursive, it's you are repeating until you reach a point where it stops, and immediately it stops. That means you'll have gotten now the value of your predictor variable, or you've gotten everything that you want for, like what you wanted from your model, to like the best from your model that you are training using the decision tree. So what happens here is at the decision mode, like you've started with the tree node, then now you come at the decision mode, then you question. So that then you ask a question to consider, like if you'll split or you'll not split. So for example, if let's say somebody is working with continuous or numeric data, they can decide to ask something like, is x1 less than 2, or is x1 or x2 is greater than 2? And for somebody maybe who's working with discrete, and discrete is always something like categorical data, maybe they can be looking on how people are, like how many people have graduate degrees, how many people don't have graduate degrees. So maybe you can say if somebody is graduated with a degree, maybe you group them to class A, and if somebody graduated with maybe a master's, you group them in class B. So that can be x2 is equals to either class B or x2 is equals to class 3. So what happens here is you'll select something like a split based on minimizing the mean squared errors. So for example, I think, let me see if I can access it so that I just draw somewhere. I think you've not given me access. Let me just request.
You don't have access. Let me
just request it.
Okay.
I think you can see it.
Yeah. I can see that. Let it open. Yeah, let it come. Yep, it's done. Can you try it out?
Okay, let me open again. Just a minute. Yes. So this is what happens. Let's say, for example, maybe we have something like 200. Like for example, here, let's say we are 200, and maybe we want to see maybe if maybe people are, maybe our height is greater than 56, or how many people their grade is lesser than 66. So of course, for this data, we can decide maybe to create a split whereby maybe we can look at the first 70 and maybe you can look at the other 30. So for here, we'll check maybe if these ones, let's say these ones are x2, we can check if they're less than d, and here we can check if they're greater than d, and maybe this d, it's maybe our height, which is 53, and also this one is 53. So you'll come here to see if that is where, let's say for example, that is where you've splitted, and maybe you want to train it, like for example that decision tree, and you want to determine if this x is greater than that d, and if this x2 is less than that d. So what happens here, they're saying that after you've split this and maybe you've reached at what you wanted to get, you'll go and look at the MSE of this one, then you come and look at the MSE of this one. So after that, like usually make sure that the sum of the MSE is minimized for all the split, and you keep that split. So for example, if this one has a small MSE, then you'll have to keep this one. And if this one has a smaller MSE, then you'll have to keep it. But the one that has a greater MSE, you leave it alone, then go with the one that has a lesser MSE. Then from that, you'll continue like doing that process of 1 and 2. You continue until now the criteria is reached, whereby you get maybe the minimum number of observations available. Like you have it now available to you because now you've gotten which of the splits has the minimum mean squared error. So the goal here is that the like last subset that you get must have like a marginal improvement of the MSE that you're looking for. So that one that has a minimum MSE is the one now that you'll retain now after you've done all of the splits. Then now you pick that to be now the best one now to use. Yeah. So that's all about that.
Okay, any question or we continue presenting? Okay, you can see people saying that they are good. So,
Yeah, unless somebody has a question. Actually, decision tree is just you making like the goal here is just like you're making a decision on something. Like you want to pick after you trained your model, you want to pick after splitting, you want to get something that will give you a model that is performing well, like it's of good performance. So the goal here is at the end of the day, you must get where the minimum squared error is minimal and not large. So if you get like you went the first split, then you checked out and again, you can go on now on the split that has the minimum squared error. Then you go again and make a more split because now you want to minimize, like you want to get minimum number of observations that will be available to you. And those observations should have an MSE that is very, very small so that at least your model can perform like better. Yeah.
okay, so my question will be, Linda, for example,
Yes.
this is where we're making the decision.
Yes.
And our value is x is 4.5, right?
Yes.
So how do we determine that maybe this value of x is less than or equal to 5
You'll
as
calculate.
the lowest MSC?
You'll calculate to check.
Calculate to check.
Yes.
Okay, thank you so much for that.
So definitely, what you do is that, of course, you will have trained your model. Okay, though I'm going in front, but you'll have already trained your model using the decision tree regressor. Then you see you'll go and fit it. Then you predict on the X test. Then after predicted on the X test, definitely you calculate the MSE whereby you're looking at your predictions and the Y test. Then now you'll see if that is minimizing, like if that will be able to minimize like your MSE, and also looking at the how is it called, the RMSE. Then if you get at a point whereby you have that is large, then that means your model is not, like it's less accurate, like the predictions are not good, and therefore that means you can go back and do another tree. Or if it's not performing well, that is where now you can decide maybe to prune your tree or make some adjustments. Yeah.
Okay, thank you so much, Jebet.
I wanted to ask a question to Linda about the minimizing MSE on the split. Doesn't the model do that for you automatically? Like the fact that you are using Python, maybe?
Yes, it does it for you.
Yeah.
Yeah.
Okay. Thank you.
Okay, thank you so much. So let us continue. This process is repeated iteratively across all subsets until a desired stopping criterion is met. Ultimately, partitioning results in a tree structure where data is divided into distinct subsets, enabling the prediction of target variables for new observations based on their characteristics. So we have an example here. Imagine we have a data set containing information about students, including their study hours and test scores. Our goal is to build a regression tree to predict students' final exam scores based on these two features. study hours, and test scores. First, we start with the entire data set at the root node of the tree. Our objective is to partition the data into subsets that are as homogeneous as possible in terms of final exam scores. Can someone make us understand the first step? Anyone? It's not supposed to be maybe Linda and Jebet alone. We are all equal here. Anybody who can explain that?
Homogeneous in terms of the methods, ama homogeneous in terms of what?
So, let me read up to here first. We start with the entire data set at the root node of the tree. At the root node of the tree, here, where the entire data set is. Then, our objective is to partition the data into subsets that are homogeneous as possible. We are partitioning the data into this side and this side, but they need to be into subset. These are the subsets: subset 1, subset 2. They need to be homogeneous as possible.
Okay. So in other words, if you're taking one method, you should one. If it is decision tree, it is decision tree.
Yeah, basically that is the method that you're using.
Yeah, you have to select one method. It's decision tree. If it is booting, lagging, bagging and voting,
and all that.
choose one. Yeah, that's what it means. I think that is what.
Okay, can I comment too?
Yes.
Yeah, Jebet already said it. Like in terms of characteristics, what this part has should also be duplicated on the other part. That's what the homogeneity is talking about.
Yeah, exactly. They need to be homogeneous. The two subsets, they need to be homogeneous. Like we need to minimize the biasness, not like we are favoring one subset and the other one. They need to be homogeneous from my understanding. I think there's somebody who has raised a hand. Glorine, yes?
I think from my understanding, homogeneous subset. So I'm thinking it should be of the same group, like of the same predictor variables, if that makes sense. So we should not have.
Yes, I agree.
Yeah, we should not have different values like for X3 in X2.
Yeah, thank you so much. Ferris says, I think homogeneous is referring to purity. Yeah, thanks. Did you have a question, Mildred, or I continue? Time is also not on our side, so that we can do this example.
No, continue. But I would like to hear Ijoma is saying no. I don't know why.
You'd like to hear Ijoma speak? Okay.
So I'm saying no to to purity because if you just say purity, that homogeneity is purity. Purity, from my own understanding, is I think it doesn't give a clear. We all have spoken well, but it doesn't give a clear picture of what homogeneity is, because just like you explained, it's a thing of the characteristics. What you have in this part, you should have in the other. Just like Lauren also explained, that it should be of the same group of variables, kind of. So when he said purity, I was kind of thrown off. I don't know if he can. Is it he or she? Sorry, I don't understand the name. Maybe you can explain why you said it's purity. Sorry.
You can unmute and explain, Ferris, if I'm not wrong. Ferris Namax. If you'd like to explain, or I continue reading. Okay, let me read. So the second step, we consider each predictor variable. Let me return back. Yeah, we consider each predictor variable, that is study hours and test scores, and evaluate potential binary splits. For instance, for study hours, we might consider splitting the data at different values like 3 hours, 5 hours, and so forth. Then step number 3, we calculate the mean final exam score for each subset resulting from the potential split and compute the mean squared error for each side of the split. The split point that minimizes the MSE is selected as the best split for that predictor variable. We compare the best splits across all predictor variables and choose the optimal one. This becomes the decision rule for the current node of the tree. 5, we divide the data into 2 subsets based on the selected split, creating 2 child nodes. 6, we repeat step 1 to 5 for each subset until a stopping criterion is met. This could be a predefined maximum tree depth, a minimum number of data points in a node, or other criteria. I believe all these steps, they're automatically done when you call on that function of the decision tree. So does anybody have anything to explain? Okay, through this process, the regression tree partitions the data into distinct subsets based on different combination of study hours and test scores. Each partition represents a different group of students with similar characteristics. This partitioning allows us to predict students' final exam scores for new observations by traversing the tree and reaching the appropriate leaf node based on the input trees. So for us to call upon the decision tree, first of all, these are the functions that I've seen for some time. I'm trying to move now a bit faster. Import NumPy, pandas, and matplotlib. So we need to import those functions. Let me not try and import, because Linda had already done this. Let me just try and explain. So once you have imported these functions, then we call upon the data set, and our data set is salary underscore data. Then we save it in a variable known as data, and then we call upon the first 5 rows. So you can see you have years, experience, and salary. Years of experience and salary, I guess so, right? So these are the first 5 rows. And then here it says, we will be using the value of years of experience, that is the independent variable, to try and predict the salary, that is the dependent variable. So our independent, it is like independent, always it's usually on the x-axis, and then the dependent on the y-axis.
Just a minute, like the explanation that I gave out at the top, the one that has exam test scores, that one was just trying to explain more, like to understand it better. But now the CSV file that I'm using, it's now using for yes. So now so the CSV file is different from what was explained above. What I explained above, I just wanted you to get more of what is happening, like as you're splitting from one decision to another. And then I just used a different salary data CSV file. Yeah.
Yeah, so we are using the salary data file, and this is how it looks. You have two columns, years of experience and then salary. So our years of experience here is our independent variable, and then our salary is our dependent variable. So first and foremost, we will like store our years of experience in a variable known as X in caps, capital, and then store our salary in a variable known as Y, and that is the dependent variable. And then here we've just tried like to create a scatter plot. You can see that scatter plot. So our title is years of experience, and then years of experience versus salary, and then our X is the years of experience, our X label, and then our Y label here is salary is here. So I think here is just Linda just tried to create a scatter plot so that we can see if there's any correlation or any relationship. And maybe if I may ask, do you have any relationship from this scatter plot? Anybody, do you have any relationship?
I think there's a linear relationship.
Yeah. So even from the scatter plot, we can see that there's some linear relationship here. So the next step is to split our data set into train test split. So from scikit-learn, we are going to import train underscore test underscore split, and this function will enable us to split the data, the salary data here, the one that we have uploaded here, into training and testing data sets. So as usual, you can see this is the function. We have the x underscore train, x underscore test, y underscore train, y underscore test. Then we call upon this function here, and then we reshape our x values, I think, to make them into a column data frame. And then we will split in terms of 80-20. 80 is the training data and 20% is the testing data. That's why you have test underscore size equals to 0.2, which is basically 20%. And then the random state of kept it as 42. Just like I think it was Waswa or Win Westland some few weeks back, that it's something that most data scientists just use, and this is just to make this function reproducible, so that if anybody else uses that, it will still like split the data and give you the same values. So after doing that, then we build the decision tree, and this we import the decision tree regressor class from the tree module of the sklearn library, which will help us fit a decision tree to our data set. So we need this class from the tree module of the sklearn library, which will help us fit a decision tree to our data set. So this function, it does that. From sklearn.tree, import decision tree regressor. After importing our decision tree regressor model, we have to instantiate the model, right? This step also allows us to set model hyperparameters such as max depth. You can see max depth here. Max depth of the tree, that is the number of nodes between the root node and the leaf node. These number of nodes here. This is the root node and this is the leaf node. Is this a leaf node really? Linda, the terminology is the same as the leaf node.
Yes.
Right?
Then
Yeah.
just 1 minute. Yeah, and then just 1 minute. So Lazarus, you can decide to go on your X variable, like when you are now setting your dependent and independent variable, you can decide to form it like a T first by using the two block brackets, like the 2 square brackets. Then that means when you go down there, you won't reshape it again to a 2D array. Or you can decide just to leave it with 1 square brackets. Then when you go uko chini, there down, you remember now to convert it, because if you don't, then it will throw you an error, because I think it will tell you something of maybe we don't have something of the sort. So -1 to 1, it's reshaping. Then I think 1 to 1 gives you a 1D, if I'm not wrong. Yeah.
Okay. Thank you so much, Linda. So after importing our decision tree, just like you were saying, we have to instantiate the model the same way that we were doing with the linear regression and the multiple regression. Reg_tree equals to decision tree. So this class here and then into brackets, without this, I believe that is what we call instantiating. Then this step also allows us to set model hyperparameters, and this is where they break them down. The max depth, and this max depth, what it does is like sets the number between the root node and the leaf node. So if you say like 2 here, we'll see how it will produce 2. So the number of nodes, these are the number of nodes here. Between this is the root node and this is the leaf node. So I think these are the number of nodes, this one and this one. But you can come in also, Linda. Let me try and minimize it so that you can see the entire thing. Yeah. So Linda, maybe you can come in and explain. Yeah.
Okay, so after you've instantiated your decision to regressor, so you telling it, like giving it a maximum depth of is equals to 2, it's like now you are telling like the depth of the tree, like you to determine like how many splits it can make before reaching the leaf node. So for example, if you say it's set to 2, meaning your tree that you are building will have a maximum of 2 levels of decisions. So that is what it means. So it'll go to decision 1, it splits, and then it goes to decision 2, it splits, then it stops. When it stops, now it picks between the final, then it measures now the MSC, and then it picks now which one is the best. So that is just what means to that. And then when you say maybe random state, now that one is reproducibility, like you're trying just to make sure that the model is giving you consistent results on the training data. Yeah.
Okay, thank you so much, Linda, for that. So that was the first thing here. Let me try and maximize this. Max depth, and then random steps, the way they've just explained. So the criterion is the function to measure the quality of a split. The model uses the mean squared error to measure the quality, and then the random state is something that have been explained. So this is instantiating the regression tree model. It's like a similar thing like the one that we've been doing in the past. Then we need to fit the model, just the same thing that like you're doing in the past. So you can see here, this part here, now we come and say dot fit, and then we put our X train, like our training data, and then you have the X train and the Y train. One of the things that I did not understand here, maybe somebody can try and explain to me, is this like a common thing, like we need to write the way it is when using decision?
No, that's a variable. That's a variable.
That's
You
a
can
variable.
I name it chicken.
Yes, you can even write
No,
it.
it's not. Even when we were doing linear regression, you remember we would use model, we would use like, it depends.
Exactly. Yeah.
You can just, it's easier to use this so that then you can remember what you are referring to when maybe you're doing a very huge, like a big know a lot of lines of code, so you're able to remember, oh, this meant this. Because say if you use a different word, it might be hard to remember. That's why they use this.
Yes,
Okay.
exactly.
Yeah, thank you so much, guys. I believe that one was Nemo. Nemo, PG, you confused me. Okay, it's fine.
All of them were talking.
No worries.
Yeah.
So, in a Jupyter environment, please rerun this cell to show the HTML representation. Or
Sorry about that. I think if
what do you want
are
to mean
supposed-
here?
okay, because I know if you run it on your side, you'll get errors because I saw you. But you need to get now
No,
the.
I can do that. I just
Okay, you can,
decided
okay, you can
like
do that. You can run it so that it won't give you that issue. It will give you now how it will fit the decision tree regressor model. Like you'll see it the way you are fitting the linear regression model. Then you are getting something like a table up or something like a table there. Not that.
oh
just
right.
Do you know it? Or I can
Let me-
showcase for
No. Let me just start here because I was feeling like not to run these things, but let me start on top here because the data set and this file they're in the same folder. So let me try and run so that we can see what you're talking about. Yep, I think then I should run this one. Run this one. Yeah, this thing here.
Yes, that's what I'm talking about. Yeah.
Okay. Yeah, so guys, you can see the decision tree regress.
So that means you've fitted your model now. So now your model is into place. You've fitted it. That is what it usually means. Yeah.
Okay, thank you so much, Linda, for that. So here, after fitting our model, we didn't have to import the plot underscore tree for us to be able now to plot that decision tree. From my understanding, Linda, from the way I was reading
Yes.
content, right?
Yes. This one is just now giving you how what is happening. You can just plot like the tree to look at what is happening, but it's not a must. Just
not a
for
must.
more illustration, just to see what is happening. So when you want maybe to plot and see how the tree is looking out, you just do it like that. Yeah. Okay. Lazarus random is equals to 42. It just means you're so that. Do you remember when people said it should pick? Was it picking 42 and then it goes so that it doesn't repeat or something, like to make it consistent? So you can decide even to say random state is equals to 2, random state is equals to 34, random state is equals to 100 or 101, but 42 is the one that is usually used. There's somebody who discovered about it because there is something that is about it. Let me just scratch it for you, then I'll give you why it is used, but it doesn't mean anything, like it's not constant. Yeah.
So let me try to explain it to Lazarus. I think it was Vin who explained it very well some few weeks back. So setting a random state equals to some number. Basically 42 is like the one that has been accepted with most of the people, but setting it to either number, be it a 0, 7, 1000. So if anyone else comes and picks this data and then sets that random state to the same value that someone else had used, be it 42, be it 7, be it 1000, it will split that data the same way, the way that it had done before. Like it's something reproducible. I don't know if Vane is on board to try and explain this once again. All right, go ahead. Okay, so let me try and go ahead. So, Linda, you are saying that it's not a must. This is just like to try and see. So our figure is a 9 by 9, and then we are running this function. There's an underscore here, meaning that you have left it open, and saying that equals to plot underscore tree, then regression tree. We are plotting our regression tree. Then feature names, they are the years of experience, and then the field equals to true. These functions, they're hard for me to try and think in my head but I can at least know what they're saying. So after running this function, this is what it produces. Let me try and minimize kidogo. Yeah. So that function is the one that it's like giving us the decision tree. So we had set our with a decision tree, Linda. Like here, max depth equals to 2, meaning the number of nodes between the root and the leaf nodes, they're supposed to be 2. So are they 2? Linda, are these 2? Hope I'm not alone on this call. Okay. The other us, I can see you.
Sorry, I was talking and my mind. I was talking and I didn't realize about mute. I was asking you. You can look at the first, like on the root, like how many decisions are on that are here.
Yeah, because I want people to understand this thing here. That
yes, that's why I'm asking. That's why I'm asking, like how many decisions are there, because that is where we should be coming from, so that you understand
decisions? It. Like
yes.
From the root node, we have this is our first decision, right? Here.
Yes.
Then this is our second decision. And then these are the...
So we have 2 levels of decisions.
Yeah, 2
exactly.
levels.
If you have 2 levels of decision, yes, so that means we have 2 splits. From those 2 splits is where now our model, now our decision tree regressor is now coming now to pick now from there down to see which one will now be our best. Then it will determine now that from the 2 splits, which one now is giving us the minimum squared errors. Because you told it to split 2 times. So that is like, it is just having 2 maximum levels of decisions. Yeah.
Yeah. So thank you so much, Linda, for that. So I believe guys have been able to understand this, the meaning of max depth. Random state, we have understood. So we had our data here. So the feature names, these are the feature names, right, Linda?
Yes.
Yeah. So years of experience is less than or equal to 5. Then the squared error was that one. Then samples was 24. Their value is that one. I'm trying to read in between so that I also understand this.
So the top one is the root node, right?
Is the root node.
Yes. Then it goes now for then maybe it looks for years of experience. Then it gives 2 splits. It checks for years of experience, which is less or equals to 2.55. Then it goes to check also for years experience, which is less or equals to 8.3. So it makes decisions on those the 2 nodes, because those are the decisions.
So basically, then when it's making
the 2 decision, yes.
So when it's making the decision here, just from the way you had explained earlier, it will like follow the route that has the MSE is low, right?
Exactly.
So if you try and check
the overall,
like, okay, I want us to compare these 2, right?
Not the on the decisions. I think now that we can, let's go and see the leaf nodes.
These ones, the leaf nodes.
Yes. That I think that is where now it will make the decision, because now it has already gone from the first decision, then it split, and then it went to the next decision, then it splitted. After splitting, now it will come now to look at the remaining parts. So it will follow the first decisions, go through it, then go to the second decisions, and then compare which one gives a minimized MSE. Then picks that one out to be our like it picks the one that has a minimum, so that our model at the end, like it gives like a better model that is good, something of the sort. Yeah. So right now you can't know which one will be. I don't think you can be able to understand unless now you get the Is it maybe, yeah, Jebet, you can explain maybe better.
I think this is already our final model. I don't know if you can run for me the like our data, like print data dot head 10.
Where can I do that?
Just do it. Just do it.
Below here.
Just do it
Yes.
above
Yeah.
the tree. Yeah,
Above
not
the
just that.
tree. Above the tree.
Above the tree. Above the tree.
Why is it coming down? Or I need to print like here.
You can just do it there, no problem.
So dot head
10.
10, huh? Right.
Yes. Now you see we have like 1.1, we have 1.3, we have like we just have like random numbers over here on the years of experience, right?
Yes.
Then now when we go to our tree, just go to the tree,
The entire tree.
like here.
Mm-hmm.
I'm
The
looking
final
at
decision or what? Where?
like where is the first decision?
Here. These two. Here or
Let's start with these two over here,
mm-hmm.
which says years of experience is less than or equal to 2.55. Why didn't it pick years of experience, let's say less than 3.5 or less than, any other number that is in that list? It's because it has gone through the whole list, calculated the possible splittings, and then it calculates the minimum, the MSC, and then it has found that splitting at 2.55 is the one with the minimum MSC. That's why it chose it. I don't know if you get what I'm saying.
No, I'm not getting it. So you're telling me that it has chosen like it goes through this other side here. That is,
no, I'm not saying it goes through this other side. I'm saying how it chooses to make the decision to be 2.55 and not any other number.
Mm-hmm.
Like cannot like why was it not 3 or why was it not 1? It's because it has already done that. Like the model does that in the background, and then it chooses the one that has the lowest MSC. So for here, like here you could have a lot of possible trees that could be possible to be plotted.
Yeah, I understand.
So now when you calculate the MSC, we choose the one that has the lowest MSC. So 2.55 was getting the lowest MSC for this particular decision. So every other decision it does the same.
Okay. So from there, like from here, from this decision tree, can we be able to spot the answer?
Answer to what?
Like the one that am I asking the right question? Like basically, what are we first of all like? What was our criteria?
So you see now, this decision tree, the thing that is going to help us is when we are trying to predict. So now, for example, I come to you and I tell you my years of experience is 5. I want you to determine for me my salary. So you will go back to your decision tree that you have already fitted with your data, this final tree. And then now you start following, like go back to the top, the original where we started here. So I tell you my years of experience is 5. You come here and say, your years of experience is 5, it's less than 0.5, so let's continue. Go to the next one. Is it less than 2.55? No. But is it less than 8.35? Yes, so we use the left side. Then we go down here. You ask me, I said my years of experience is 5. Is there not a decision here? So is it less than 8?
Yeah, that's the thing that I want to ask. Like, if you look at this decision tree, can you go to see?
Jebet,
Yes?
let me ask, Ebu, just repeat what you've said because I've been waiting for this to understand this country.
Yeah.
Yes. Hi, Jebet, mini Jebet.
Say hi.
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 Hi. Ebu explain again, because at a meal it figured somewhere I was like, I'm not understanding these two things.
So now how
Yeah, and yeah,
like,
go
what
ahead,
do you
Jebet.
want? How do I start?
As
Okay,
in,
let's start here, Jebet.
Start from the top, yeah.
Jebet.
Start from there.
Jebet.
Yes.
Yeah, Jebet, let's start here. Let me try and maximize it. I'll minimize it. Nemo has come to you and she has told you that her years of experience are 5 years.
Yes.
So we start here.
Yes.
Yeah.
Mm-hmm.
So we are waiting for you to try and explain.
Oh, okay. So now
Most years experience is 5 years.
years of experience is 5 years.
Yeah.
Then so I come to my tree. Yeah.
Mhm.
This tree has already been fitted. It has already been modeled.
Mm-hmm.
So I'm using this tree to predict if your years of experience is 5, how much is your salary? So is it less than 5? 5.5? Yes, we go down here. The next question. Is your years of experience less than 2.55? You said no.
No.
So we go to the other side, which is your years of experience less than 8.3? Yes.
Yes.
Then we go down there. Let's go down. So this one, I'm trying to see what we are supposed to be looking at so that we come to this side and this other side.
Yeah, so that we can predict Nemo's salary.
So that we can say it's 93 or is it 11, 52, 54?
Yeah, yeah.
Squared error samples is good. So I don't know why.
For me, I think
we are making a decision based on what? Oh, okay, I get it. Go back. So here we are saying, is it less than 8.35? Yes. If it is, we go to the left one, which is like this 93,000.
You calculate the squared error.
No, we don't calculate the squared error. We are just making prediction, like we are predicting the value of your salary based on your years of experience.
So my question is, Jebet.
Yes.
You see, we have different colors here, and from the way I was reading the material, it's like these colors, they can also tell us the answer if you check on these colors. Then, if you turn and check here, does the MSc decide which decision for us to take? Because it's like on the left side, we have discarded everything on the left side, so we have only to make choices between these last two. So we have the MSc here, which I think is the squared error, and then you have the value, which is the salary now.
But I think we're just using the criteria that we have. So like now it's saying it's 8.3. So is it less than 8.3? Yes. We go to this 93,325. Is it less than 8.5? We say no. We will go to this other one.
For me, I think, and I stand to be corrected.
Yes.
But try to look at this squared error. It's it's 6,820,290, and this other one, it's 46 million. Sorry, guys. And this the other one. Let me try and see how many zeros are this. This other one is 45 million. So basically, this one is less than this one. So I think even the colors, if I'm not wrong, maybe someone who
I don't think don't use the colors. If the colors only mean the colors only comes in to check, like for example, you see like the way you specified random 42. So this thing is picking, is going through the samples and it's picking like when it's training, it's picking some of the samples, then it's splitting them. So for the colors only comes in maybe, for example, just to check maybe if how can I say, like to check if those the features that were picked, was it the features or something, had something like homogeneity. So did they have lower or strong homogeneity? So if you get whereby there is higher homogeneity, that means like a lot of features which are less or equals to maybe that value are dominated in that node. So that means maybe that color can be dark, but you don't use the colors to check if it went this side or this side. But for me, what I know is that this one is just trying us to show us out it's just showing us how the split was and what happened, but it's not giving us I don't think we can be able to see which decision was followed. So that will only go so I'm not sure. But now that all that is done in the background with now the model that we instantiated on the top. Yeah.
Okay. So thank you so much, Linda, for that explanation. Now let us put that stories of the colors.
Ambale,
Yep.
Ambale, would you mind running prediction for 5? Like X is 5, so predict, model that predict.
Fairy's hand is up, and Abika there, I think.
Sorry?
Somebody's hand is up. Fairies. Namax.
Paris, you can speak. Jebet, you say model. Where did you? Hey, wait. Where do you have a model? No.
Just go on there. Just place just put it anywhere that how is it called? The sale. You can just place it anywhere.
So we say rig underscore tree. Can I place it here?
I think she wants you to predict at X is equals to 5, right, Jebet?
Yes. I just want
Yeah.
Jebet Junior, hi.
Yeah.
let me tell you.
Are you teaching us?
Let me see. Linda.
What
Linda,
are
can
you
you give
eating?
Jebet.
Just scroll up. Again.
So
Again.
your feature model, right?
Yeah,
Or
there.
what do you want me to put X equals to 5?
So Jebet wanted to predict. You wanted to predict where X is equal to 5 or X is less than or equal to 5.
Yeah, where X is equals to 5. Like, just go to your model where you are.
Model iko juu.
Hapo kwenye alikuwa na predict hapo chini.
Oh.
Aki, I'm sorry for people who don't understand Kiswahili.
Kiswahili is our second language. First language.
Give me the code, Jebet.
Dot predict hapo kwenye huko.
Tafuta kwenye kuna dot predict ama kuna pale pa dot
Alafu
predict.
eka bracket weke 5.
Oh.
Then enter.
Where?
I don't think that can work. Let me see the error.
Ndio ni si return
Oh,
it
it's
ready
supposed
know
to
you
get-
are.
Yeah, because it's not
reshape.
or dot values too will work.
Sorry?
Try saying dot shape then into bracket -1. If it doesn't work, then you use just like that. Then if it doesn't work, we'll do dot values. Just try
Is
that.
it square brackets or not square brackets? No, cannot.
Try dot values. I think.
Assign the variable 5. Like, do X is equals to, or let's do A is equals to 5. Dot reshape. That will work, right?
Like?
A is equals to 5. Then hapo chini andika A is equals to andika A dot reshape 1 to 1.
Oh yeah.
Ni -1 ama ni -1 to 1.
1 ama -1.
Ikikata ujaribu dot values. I just want to say. Yeah.
Predict A, ingiza A hapo kwa 5. I hope itakubali
Ebu eka dot values tuone. Alafu toe -1. Toa hizo -1s tuone. Yes.
Niache. I remove everything.
Toa hizo just toa zote.
utaumia.
Hivyo.
Toa. Is it?
What
Yeah,
else?
ebu try.
You
Let me
put a
just try
bracket.
myself. Achacha ni try on my side, then toa hizo bracket kwa values. Hebu run tuone. It's still giving the
Not
same
working.
thing.
Yeah.
Just
Gari
giving.
tuendelee for now, alafu hopefully by the end of the
So
nini.
that tuone kama itatupatia the same answer. Okay, sawa. Right?
Let me tell you about the colors. The colors shows you the level of purity. So the higher the error, your squared error, the stronger the color.
Mm-hmm.
Like the darker the color. So the whiter it is, the pure the nini. So that means it has less.
Oh yeah.
Yeah.
Thank you, because I think I had passed something about colors, but I was not like getting it. That's why I was asking. That's why I was a bit confused. So thank you so much, Jebet, for that. So let's go ahead as we find out on how we can see if we can find an answer here or not. Because from the first one we were able to see to select here. So we need also to understand if it's possible or not. So people still crunching numbers. So let's go ahead. We have a fully trained decision tree model.
Paris.
No, I was just curious to ask, assuming that now you are the model,
Mm-hmm.
and you have that, I mean, assuming that you have that tree on paper,
Mm-hmm.
now which decision will you take? Considering that you also have the error values to help you to assess which output are you going to select. So
Okay, I
just in
can
this case,
answer that. So the goal of the decision tree is that you have the errors, but now it's looking at where at the split that you made, then it's calculating the mean squared errors. Now it's not looking at like the squared error. Now it goes ahead and calculates the mean squared error on the split that you made. Then after calculating that, then it makes a decision, then it stops. You see, it stops at that and decide, oh, so this split is the one that gave us a minimal MSE. Then picks that for you now to how is it called? Like it picks that and it makes now for you to use that as a way of maybe making sure that your model is performing well. So it leaves the other split alone. So that is what it does. So here it's just giving us the squared error, the squared error, the squared error, the squared error. But I think chini ya maji, if you listen to Swahili, chini ya maji, it goes ahead and does it chini ya maji, then it picks it for itself. But this is something that if you do it manually as a person, it can take you a longer time. Like it will take you a lot of time to go through until you get where the minimum squared errors are less. So that is what now the instantiation of the decision tree classifier does. I think it's that. Like it does that. The one that we fitted now, that model. So I think it does it underground. You can't see that. It makes it easier for you because if you do it, that will take you a lot of time. So I believe that is why we are trying to see if that is why we are trying to confuse. Then I think for Jebet you are supposed to convert it first to an array, then I'll predict it. So I think try and use that, and then let me know if it works for you.
Has it worked on your end?
Yes, just convert your A to np.array, import numpy, then just convert that 5 to an array, then I'll predict it.
So you can just copy the nini there and then give it to Ambale to run.
What did you to do it?
No, like I have to go and load the data to my environment.
Okay, tell me what to write. Tell me what to write.
Just give me a minute, Ambale.
Okay. So something that Jebet has mentioned is that this color shows purity. So the darker the color, the higher the MSC. So this one is the highest one. So this one is more pure, the first one. But you need to, yeah. Am I correct, Jebet?
Ambale,
Yep.
kindly repeat. I actually wanted Jebet to repeat that issue for colors because I have not understood.
Okay.
And I'm seeing 45 is less than 46.
Huh.
Isn't it? On this other side.
You're looking at samples. You're not looking at the squared errors.
Okay, so what does the what do
Yeah,
the
I
colors
think you can
represent?
repeat it because for me I was using homogeneous on my end, but I think she replaced homogeneous and purity is the same thing. So I think she can. Jabet, you can explain again about it maybe.
So the value represents the salaries.
Here, seems like we shall
Isn't
go
that?
ahead and then we come and discuss this thing. Because even me now, I don't know the value to
Yeah,
the
it's
salaries. 'cause-
confusing because
yeah.
You'd start praying.
what are the values? The values are the salaries.
I don't know. Can't answer.
I think so because that was what we're supposed to get. Just assuming that's the salary.
Me, I'm just wondering, when we go to that decision tree, I've understood up to where she's explained like it is less than 8.3. How did they come up with like the four decisions, the four predictions? Is it that I don't know what criteria did they use?
I think I think the decision tree class has inbuilt sophisticated backend IT others. I don't know that these are the best decision that it came out with from the data that was given. But now, for us to make a decision from the four answers that we have, Nemo, assist. The ball is in your court now. Because even me now, I'm getting confused here.
The ball is in my court for me, the person who does not understand anything.
Just go on. Just go on.
Okay.
I'll explain it before go and sleep.
Okay. So let us go on. We are almost finishing, and then we shall come back to where we have left so that we try and understand this. So we have a fully trained decision tree model and can easily make predictions by calling the .predict method. Evaluating the model performance. We evaluate model performance by comparing the model's prediction on unseen data, X test, with the actual output, Y test. This comparison helps assess how well the model generalizes to new data and provides insights into its predictive accuracy. We will use the MSC for this. So as usual from Skyline.metrics, we import MSC, mean squared error. Then we get the prediction. So we are storing our prediction on y_predict. So we say the variable or our tree regressor .predict, and then we give it the X test, the data that we had set, the 20% that we had set aside for predicting. And then we calculate the mean squared error here on the Y predicted and the Y test, and then we just print the root mean squared, which is basically the square root of the MSC. So then any code that we need to run here? No, I think this one the only one that we need to run.
Actually, you can also print the MSC so that you can look at it because you have it. So you can say print into brackets, then column MSC, then close. Yeah, just the same. Then comma MSC.
Yeah. Okay. Yeah. Sorry.
Hit command then. Yeah. So I think you can discuss more because I discussed the RMSC maybe you can look at MSc and so that means that between the splits that was made, this was the lowest MSc, and that is what was selected. Give us like a better performance of the model.
Sorry, I've not heard what you've said.
I'm saying for the MSc, this means that this was the lowest, like that was the minimal MSc after the splits were done. So this was our smallest MSc that we are using now to predict, you see? So that is what was selected.
Oh, yeah. Let me remove
Yeah,
this.
the
Coming
prediction
too many
and
to confuse people for nothing. Yeah, so this is our lowest MSc, and this is the square root of the MSc. So in a regression decision tree model, the root mean squared RMSc is a measure of the average deviation between the predicted values and the actual values of the target variable. The RMSc value of 639.41 suggests that on average, the predicted salaries from your regression tree model deviate from the actual salaries by approximately $13,639.41. The RMSc value indicates the average discrepancy between the salaries predicted by the regression tree model and the actual salaries of employees. A higher RMSe value suggests that the model's predictions are less accurate, while a lower RMSe value indicates greater predictive accuracy. And RMSe of 13,639.41 suggests that the model's predictions are off by approximately 13,639 USD on average when compared to the actual salaries. This means that there is room for improvement in the model's predictive performance, and further refinement may be necessary to reduce the prediction errors and enhance the model's accuracy. So I believe even from the previous discussion that we've had, MSc, RMSc will depend on what you are measuring, because now a salary range, an error of 13,000, for some it could be bigger, it depends on the context. In other contexts, maybe it could be like just something small. So visualizing the model output, general equidistant points. First, we create a range of equidistant points along the x-axis. These points can span from the minimum to the maximum x values in the dataset. We use the np.linspace function here, this, from the NumPy library to generate 100 evenly spaced points between the minimum and maximum values of the predictor variable x. This function here into square brackets, full colon, comma, np.newAxis is used to reshape the array into a column vector, ensuring compatibility with the prediction function. Can you explain this first paragraph here, Linda, if you're able? I tried to use ChatGPT to understand this newAxis and all that.
Which one? The one that is on the first one?
Yeah, just the first paragraph alone. What basically do these small? So
it's the first one that you say x underscore domain is equals to np.linspace, then the minimum of x, and then it picks the maximum of x, then 100, and then you say np.newAxis so that it doesn't run error because you've said that is an array. So basically, like, you're just creating a range of between the minimum and the maximum, and you're picking like for 100 values. So this means that the points will go from the maximum value of x all the way to the the minimum value of X, then the maximum value of S. Then the linspace is just np.linspace is just it's always used in NumPy. It's a library. So and you've told it to generate 100 evenly spaced points, like between now the way you're picking from the minimum. So the distance between the minimum and maximum, the linspace.numpy will go between those 2 points. Then it generates 100 evenly spaced points. You see, for that for your predictor variable X. So that's what it means. Then the last part that says np.newAxis, it's reshaping your array so that it doesn't give you a problem, so that it's compatible with the prediction function, which is the Y. You see, because it needs to be two arrays, so just making sure that it's reshaped correctly. So that is what is being done there. Yeah.
Okay.
Have you understood it?
Yep. Thank you.
Okay.
Then we predict the Y values. We use the trained regression tree model, this one, to predict the Y values, which is the target variable, for every point in the X domain. The predict function is applied to the X domain array, to the X underscore domain array, to obtain the predicted Y values. Then we have the plotting. We create a scatter plot of the original data points. This typically includes plotting the predictor variable X on the X-axis and the target variable Y on the Y-axis. Then we plot the predicted regression line over the scatter plot. The predicted values from Y predictions are plotted along the equidistant points in X underscore domain, creating a step function that represents the regression tree prediction. The color red is chosen for the line plot, and a label predictions is provided for the legend. So all that you have read here is in this function. Function is long. So X domain, linspace maximum, that predict for Y for every point in the X domain. Y prediction equals to regression equals to reg. This is our regression function. Then we are going to predict using the X domain. X domain is here. Then we plot the regression line over the data. So this is the figure. Then scatter plot XY. Then we plot the regression line, color red, label prediction. Then this is just the naming. Then we have the legend here. So when you run this function, it produces this. Yeah, that graph, the decision tree. Now, do you have anything to explain here, or I read fast? You only have like 10 minutes. I don't know what time exactly did we start.
Anything on this one, on this plot or on the tree? You just finish, then we wind up with the tree. And then
let me finish reading. So in a step function plot, the model's predictions are represented by discrete step rather than smooth curve. I think these are the discrete step. Each step corresponds to a particular interval or region defined by the predictor variable in the dataset. These transactions represent a decision boundaries of the tree, where the predictor variables are partitioned into subsets. So we have the advantages and disadvantages of the decision trees. The merits of the advantages: it's easy to understand and use. Number two, it's capable of handling both categorical and numerical data. It's resilient to outliers, requiring minimal data pre-processing. Then the final one, it's flexible for incorporating new features and can be extended to build larger classifiers using ensemble method. Then the disadvantages of decision tree: it's prone to overfitting, especially with complex datasets, and then requires careful parameter tuning to optimize performance. And then lastly, it's susceptible to bias if certain classes dominate the data set. So thank you so much, Linda, for writing this. This file is so good, so nice. I think we should share it with other team members so that they can also go through. So we have 9 minutes.
Ambale,
Yep.
I think Jebet had said she can explain the tree.
Yeah, that's why I'm saying we still have some
How to
minutes.
predict the tree.
Yeah, and I'll also add some sentiments on it too.
Yes, so you are here. This one did not run. So where do you want me to place, like, for you guys to see? Is it the tree itself?
Yeah,
No,
the
just
tree itself. I want
no.
us to nini the prediction of your working experience is 5 years. Just at
Yeah.
the top, like from the tree. No, we'll do this after we've done the tree. So here, on your left, it represents yes. Like, is it on my left? Yes, on my left it represents yes. On my right it represents no. Are we in agreement?
Explain why yes and no.
Like, see, that's the decision. See, I'm asking if it's able to go up where it's beginning. Like now, I'm asking if your years of experience is less than or equals to 5.5. So if you're going to the left direction, it means yes, it's less than 5.5. Or
Yeah,
it
yeah,
means no, it's more than 5.5, right?
Mm-hmm.
So here, is it less than 5.5? Yes, right? So we are using the left one,
Mm-hmm.
which is here 2.25.
Mm-hmm.
If we go here, we ask ourselves, scroll. We ask ourselves, is your years of experience less than 2.25?
No.
No, so we leave the left one, we go to the right one, which has now the R squared, which has the value as 5904, 47.44.
They said for 8.3. Sindio?
Not the same for 8.3. Remember, we left this one when we began. Like, see, here, I don't know if you can minimize this, as in you can zoom out so that we see.
Oh, I've understood. You're saying, if for example, if it says it's less than 2.55,
yes.
If it is no, it will do the squared error will be in blah blah blah. Sample value will be this. If it is more than 2.55, it
You
will
follow
be
the other one.
Yeah, understood.
So now for our case, we said it's 2.25. We said it's 5 years, right?
Yes.
So we have reached here where we asked ourselves, is it less than 2.55? We said no. So that means we're using the right one. I wish I had.
So it will be, the value will be 5. The salary value will be 59. The predicted value will be 59.
59,054, 047.44.
Oh.
Yeah. Anyone who's still confused?
Oh. Thank you. Thank you so much.
So if we do this, you can do this Ambale with the code. Let's go where we are predicting. So put A as a list, just where you are. A is equals to like a list. So put the nini. Yeah. 5. Then write the next one. A is equals to pd.data frame. Is it pd.data frame or many pd data frame?
PD.data frame.
Yeah,
Okay.
this child is the number.
And then you put a like bracket A, like, so we are making a data frame of A, this one.
Yep.
Then A is equals to, do I still need A? Do I still need to reshape A?
I don't think it's a data frame. You need to reshape it.
I don't think so. I will write print
Supposed to be but to be whatever, to div whatever.
Run that cell, run that nini. See, it's already giving us 590447. Well, that's what we found.
Mm.
Yep.
So basically, Jebet, here we were checking on this. Sorry, this value here, which says years of experience is less than or equal to 2.55, and then comparing with this one is
No,
less than
no,
or
no. Can I share so that I can use my cursor?
Yes, kindly do share.
Okay.
Don't worry, guys. We're finishing 3.
There's
Then we
just
have
we'll have Linda, then it's and here. Can you guys see my screen?
yes.
So here we were starting. My years of experience is 5 years. So we ask ourselves, is it 5.5 years? Yes or no? It is yes. So we go to this route over here. I don't know if we are up to there. We are here now. I'm waiting for someone to respond.
Yes, we're good.
So here we come here and say years of experience is less than or equals to 2.55. Is it yes or no?
Yes.
It's no because it's 5. Like it's more than 2.55. So we go through this lane up to here. As it is our final prediction. I don't know if you get me, Ambale.
Yes. Oh, me.
Yeah.
Yeah.
The main thing that I've seen here,
Yeah.
you need to understand what you're doing from the root node.
Yes.
Yeah.
So, Jebet,
Yes.
every time the left side corresponds or affirms the criteria up there. So if it's less than or equal to 2.55, the yes is always on the left.
Yes.
Okay. And no is on the right. Thanks.
Linda, you can jump in now.
Ambale, once again, can you share that code, the code that Jebet has used to confirm?
Do you want me to share it in the chat or to share my screen?
How do we stop?
Either way.
Okay.
I think they will have the notebook. Okay. So for me, I think what the beta said is right, but for me on my side that's right. But even after for me though, if I'm wrong, you'll just correct me because nobody's ever correct. So for me, like even after it has gone and the value to be, of course, it will pick the value to be 5.7, which is right. Because you're comparing it to like it was giving the threshold of 5, but at the end of the day, that is not. We are not sure if it picked between this one that has a value of 413.39 and 590 or 7, because now it branched. It made a split at years of experience is less than or equal to 255. So the model won't settle on this one. It will calculate the mean square. Then it calculates also for I think this one. Then now it picks the one that had a minimum squared error. So for me that's what I think.
But I think calculating the mean square error is when you're building the model. After you've built, like this is the final model.
So it's building, but it will pick like after you've split. Where will it end? Like what was?
So now like this model here.
After it has cleared, after it has cleared. Okay, just a minute. So after it has split at x is less or equals to 2.55, right? We are there with you, right? Just share.
Jebet can't share your screen.
Why are you getting off? Why are you getting off your screen off?
No, I want Jebet to share so that when she explains,
you can share
please can also, yeah.
Yeah, I just want to get more clarification because I want to get, if that's wrong, I want to get it off my head completely.
Yeah, where we have that tree that
Yes, that's what I want. Yes.
Yep.
Because I know the value always gives it displays the predicted target values or class distribution within that node. That's what I know. So definitely if you print the data frame of A is equals to 5, you'll get that, and you can decide that is where it stopped. That's just my thinking, because even after that, after it is split, because if you look at X is less or equals to 2, it goes this side and it goes the other side. So the other side where you've gotten A is equals to 150 point something, then the other side had 140 or something. Despite that, internally, it will look at the mean squared of the two, then it will pick the one that has a minimum squared error, because a loss error will indicate a better model performance, and that's now where it will build now our model from.
But you see, Linda.
Yes.
Is by my understanding, like when we are building the model, that's when we are using the mean square error. So after I have produced my final model, which is this one, like for like scikit-learn, it always gives you the final model as like the best model. So when it gives me the model, that model is what I'll use for prediction.
Okay.
So for my prediction, I am no longer training the model; it's done.
So here is prediction, right?
Like when I was inputting my file, I was predicting it. I was done with the model.
Okay, I don't think so.
Yeah, it is like
I think you're building the decision tree. It's just like you fully trained. This is just like you fully trained your decision tree model, so that it can easily make predictions now by going ahead to call the predict model.
No, right? It's just the same way when you're building a linear regression model. After you've produced your final model, so that's the one that you'll use to make prediction.
Yes.
Like even if you do it by hand.
Yes.
Like how you extend that line of feet.
Yes.
That's how you make your prediction.
And that's what
after I've used my training data to train my model.
Yes. So this tree is trained, right?
Yeah, this tree is already.
And how can you be sure that, okay, are you making assumptions? How can you sure that it picked this node just because you tested it at 5 and said it went outside?
See, because it's already showing us how it's splitting, like the splitting criteria.
Okay,
like, It's showing us if it's less than 2.5 or not. You choose is it less or not.
Which all of them. Then after that, you get to split, right?
Yeah.
Yeah, I think I can also like understand what Linda is trying to say.
Yeah, there's something that
because you see, like you have just given this regression tree some data. Then you have split that data into 80% training data and 20% testing data, but we did not give it prompt that we are looking at a specific value. We just gave it that, and then it has given us a decision tree. So it has given us the best values possible.
Exactly.
So if you try
X is less or equals to 5, it just picks randomly. So it's just giving us like what is happening. So you basing your argument on X is less or equals to 5, then you going to check 5, definitely you'll get that. But now that is not, like, if you look internally, like that is not, even if you check well, that is not the last leaf it will stop at. Because even if you compare the R squared of the one you've gotten and the another split, because if you check X is less or equals to 2, we also have 2 splits.
But that's going to be my last split, since you said that the maximum depth should be 2. So my splits are only going to be 2.
And you have to, okay, you can share your screen for a minute. Okay, guys, I know I'm disturbing, but just a minute.
No.
No, like we're also learning.
Linda.
Yes.
Is coming from.
Okay.
Yes, Kito.
Okay, I think I understand Jebet.
Yes.
Because the model has already been created. And
it has been trained, right?
Yes, yes. So
Uh-huh.
we already have our model.
Yes.
So right now, we're
We don't
trying to
know.
predict some salary based on years of experience. Since you have the
Yes.
model, someone might come and ask you, I have 5 years of experience. So what is my salary bracket, or what do you think my salary will be? So since we have the model, we can now go ahead and predict that person's salary based on the years of experience the person has given you. So I think that's how I'm understanding this. Because we
Okay.
already have the model.
I think let me.
Okay,
I
Kito.
will.
Kito,
Yes.
can I say something?
Yeah.
Yeah, I understand you, understand Lina, understand everywhere. But I'm kind of like inclined to Linda's side, because when you are creating this decision tree model, we did not specify any specific value of the variable that we're trying to predict. We just gave it data, and then it has given us a decision tree, like with the best split possible.
Yes, it has
Apollo.
given us a trained. It has given us a trained decision tree. So if you look
Yeah.
at here where x is less or equals to 2, if Jebet could not go ahead and go and check, let's assume like no mathematics. If she could not have gone and picked, like converted A to a data frame, then give it 5 for her to decide.
Linda.
Yes, just a minute.
Okay.
And also it's moving this side. You see, we have at x is less or equals to 2, we are splitting this side where you got the value of 5. And also we are splitting on this other side. And if you check also this other side, the mean squared error is lesser than the one that is on the right. I don't know if you are seeing that.
Now,
So check the mean squared error of the two. Where you got where you got, can you enlarge this screen? Where you got 590.07, that is the value. And remember, okay, now give us what does value represent? Because for me, I know the value always displays the predicted target values or a class distribution within that given node. Right? Yes.
Okay.
So it's giving us the
Can I say something?
Yes, please. If I'm wrong,
okay,
I'll just move that from my head. Yes?
For me, I think you are both on the same page, and I think what Jebet was trying to demonstrate here was just like the someone is talking. Okay,
No, you kindly go ahead.
Okay,
wait a bit.
Oh,
Wait a bit. I've now taken fully ownership. I'm now in charge. I'll be letting people to speak. So we're starting with you. Kindly go ahead.
Okay. I believe Jebet was just trying to demonstrate that the figure we are seeing here has already been trained. And therefore, irrespective of we call it the Y, we call it the, what name do we call Y? The dependent variable we are trying to bring will still give us the expected answer. And she did not mention that the 5 years experience is the last node. No. So even if
Jebet, you said that, right?
I said if we are predicting 5, and now Linda,
Yes,
I want you to give me an example.
Yes.
Where you think it will not, Alafu explain how I think it will pick the answer.
Okay, let's do
so
that.
We do it practically.
Yeah, wait a bit.
Let's do that at the end.
Wait a bit.
I'm sorry,
Kito, your hand was up. I don't know if you want to ask a question now, or we first of all allow these 3 people to argue for 2 minutes and then you come in.
No, I was just thinking that maybe you said you don't understand where the 2.55 came from. So I was thinking maybe it came because we gave the model instructions that it should have a depth of, I think it was 2, I'm not sure, and a random state of 42. So my thinking is maybe the 2.55 and the 8.3 was the optimal model way to say that this is the optimal way to create this model.
Exactly, that's right.
And that is what actually all of us are trying to understand here. it means the same thing because
Mhm.
the 2.55 is just a value. Like in mathematics class, we have got a function. And so if we replace maybe x by 2.55, then the expected output is that 52 we get. And then if you look at how it separates, like at that decision node, then one goes left, one goes right.
Mhm.
It says that there is a year of experience less or equals to 2.55. Then that is at a point we have to make a decision. If it is less, then take this direction. If it is more, then take this direction. So if maybe the year of experience is 0.5, then we would have taken the other direction. And then we move up to the point when we get now exactly 0.5. What value will it have? Then the value will probably be less than the 52 we are talking about, because the value there is the predicted salary. If one has got 2.55 years of experience, then the expected salary is about that figure that starts with 52. And then if it is above that, that is where Jebet, I believe, picked the 5 years of experience, and the value down there was showing a relatively higher figure, that is 59. Of course, if you look at it logically, if you have got 2.5 years of experience, then the salary is relatively lower as compared to someone with 5 years of experience. And I believe if it is cascaded downward, no matter how long it will take, then the decision will still make sense. But I believe the structure here we are seeing has already been, the model here has already been trained. So I believe both Linda and Jebet are on the same page. It is only that maybe Linda understood that what Jebet meant, that the 5 is the last node, where it should not be.
That's what she said. That is the leaf node. Okay,
And-
just give me a minute.
Yeah, can I?
Just give me a minute, Ambale. Just a minute. I want
Okay.
to hear from Abdi. Abdi Kadir, please. If you are there, I want to hear from you.
Okay, Linda, and actually my main question here would be for Jebet. I wanted to know, I don't think in this she is answering any question. It's just trying to help us in figuring out if you understood the MSC and the sample, how the sample is distributed. So I wanted to ask her, what is her understanding on each node when we say MSC?
But can we come to an agreement that this is going to be our final tree? And that no matter what, like the values we are going to have are only going to be these 4 values, no matter how we test it, for as long as we are using this tree.
Yes, for me,
Yeah.
For me, I will say this will be the final tree. And can you allow me 30 seconds to explain something?
Yeah.
First of all, when we gave this decision, when we gave this decision tree function, this data, first it took that data and split it into 80-20. Then it checked on the MSC. It went again, then did that for several times, which I'm not aware of. Then it took the best split, which has the minimum MSC, and then that minimum MSC, it had years of experience, 255, and then on the other side, years of experience, 83. So it, in the background, it separated this data into maybe even 100,000 times. But this was the best. So I will agree with you, Jebet. This is the best that we can have. Thank you.
So my question goes to Linda. Linda is still there?
Yeah.
So I wanted you to kindly explain to me, like, you're saying that if I give it a value, it's going to retrain it again.
I didn't say that.
Okay.
I just said that if you look at x is less or equals, actually, just get me very clearly. We checked for the first one. We said x is less or equals to 5.5.
Yeah.
We went to catch. We left the right side. We went to the left side, right?
Yeah.
Then after we went to the left side, we narrowed down to two leaf branches, which are the terminal. We have the first terminal, which gives us a sample of 5 and a value of 413, 339. Then on the next one, you have a sample of 9. Then you have a value of 59,047, right?
Yeah.
Let's assume you didn't do what you did. Like you didn't go and find the value of A.
Yeah.
What could be your final leaf node there? Like we didn't
the same. Now, can we use my year of experience as 1, for example?
Okay, just a minute. So that is where I'm saying, even because you've tested, and I don't think somebody needs to test that because that is done by the incendiary model that you've done. I was just looking at, because you have 2 leaf nodes, the one with 413 and the other one with 590. So for that, we have to look at the squared errors, and of which we are not sure. Like we are not sure about that. But I've not refused that will be final or not. I'm just saying something like you can't be sure which one will be picked because remember, maybe if you are training and you have so many, you could be having so many nodes at the end. You can't go on testing. So for me, I was thinking that between these two, because this is a trained tree, a trained decision tree. So it goes ahead. What will go ahead is just looking at the squared errors between the two of them, because that is what we are doing. So after that, then now we go and predict. So but now we are not calculating, but you are not doing it like right now. Now that will be done at the end.
So my question is, here in this situation, how will the squared error help me?
You just look at you look the first split as a minimal squared error.
So for example,
squared error here means MSE actually.
No, I want if we are saying, for example,
yes,
I want us to pick something.
I think you're getting there. Yes.
It has a high MSE. So for example,
yes,
can we use this node over here?
So, but we didn't pick that node. So just go back.
I'm saying, let's say my years of experience is 10.
Yes.
Not 10. Is it 10? Let's say 5.
Yes.
Not 5. 7. Sorry.
Okay.
7. Sorry. Yes. So in my explanation, I would say, my years of experience is 7.
Yes.
I come to the first node over here and ask myself this question. So this is my decision node. Is my years of experience less than or equals to 5.5? Yes or no? Remember, it's 7.
Yes
or no?
Yes.
Is it less than 5.5?
No, it's less. It's less.
Is it less than 5.5?
No. You placed another node at the top.
No, it was there. Like this was the tree.
Okay, 7 is greater than 5.5.
So that means I'll take this root over here.
Yes.
So if I come here and ask myself, is my years of experience less than 8.3?
No, it's not.
It's not?
Yes.
It is less than 8.3, Linda.
7. Yeah. I'm comparing it to 5.5, sorry.
So is 7 less than 8.3?
Yes, it's less.
So if it's yes, I take this one and my answer will be 93,323. That will be your expected Y.
Okay. I think I'll just go with it.
I know you can go and
I'll search more on it.
Search more on it.
Because we won't finish.
Yeah, I think before Linda, before you start tomorrow's class, I think tomorrow's session we can actually have a look at this. And I tend to agree with Linda. I have my explanations that are actually somehow hard to explain right now, but I'm sure I'll have something tomorrow evening before the session starts. So yeah, we can revisit this tomorrow before we start the second session.
Yeah. Thank you, Abdikadir. We had John Warutere hands up. I don't know if he still wants to ask any question.
Oh, I had a question, but I think if they'll explain it tomorrow, I'll wait for tomorrow. Because it is concerning what they were saying about the route that you are taking and the MSc. I'll ask my question tomorrow. No problem.